again. Greetings to all of you. My name is Hasnain Hassan, and my groupmate in this final year project is Mohammad Amin, and the title of this project is Impact of Integration of Jhimpir Wind Farms in HESCO-NTDC network. This project is supervised by Engineer Ghulam Akbar and co-supervised by Engineer Abdul Rauf. As we know that the Pakistan cannot increase its production via coal or hydropower plant due to political and international issues. As we know that the non-renewable fossil fuels are depleting day by day, and this leads us to the wind generation. And this project is all about the simulation of the interfaced wind farms using PSSE software to understand and comprehend the active and reactive power flows. Power flow, or you can say the load flow, was done to analyze voltages at different buses, lines, flows in the network, and system losses too. And one of the main method was applied also. The N-1 contingency was applied to understand the worst case scenarios of the system interconnected system. This is our final draft of the SLD diagram. Well, why we need dynamic analysis in this project? So in order to understand the dynamic analysis, first we have to understand the definition of it, where the identification of weakness and strengths of synchronously connected system is known as dynamic analysis. Dynamic analysis is also done for the future system planning purposes, so to investigate mutual impact or interaction of the incorporated areas or a specific region. Observational system under short circuit fault and burst fault are major elements of this project, so that the observability region should output the worst case scenario consequences such as the disturbance in frequency, VAR, KVAR, and voltages, etc. Whereas the LVRT capability is to alert generators and other special purpose devices and defense schemes to initiate it fault time. Well, the motivation of this project was, as we know that the wind is unpredictable source which creates problem in generation and interconnected system. A fault due to high speed wind occurs which can lead to generation failure and can impact the total outflow. The output sometimes may not be available to meet demand. Inconsistent flow of power can reflect the impact of observability region. Whereas the problem statement is that the possible cause of voltage instability and frequency disturbance and their behavior, to find out the impacts from different applying different techniques such as load flow, N-1 contingency, and dynamic analysis, as I have explained. LVRT capability is the system for the protection purposes used in the major industries to protect the system. Overall impact of the wind generation on voltage, frequency, and KVAR, that how they behave. Well, the literature review is concerned, so the wind power plants cannot alone be used as we know it, because it can have negative impact on such ingredients like grid integrity, power quality, system security, system stability. It provides imbalanced power. One of the example was happened in the Germany in 2004, when they lost 4,000 megawatt of power in wind generation, and they provided a solution of backup plant. Whereas the technical losses are concerned, these are the inherent electrical properties of the system components. Copper or variable losses are dependent on load current and occur in conductors, cables, and transformers, and are given as overloading, unbalanced loading, poor loading, power factor, and improper reactive power compensation cause increase in current, thus contribute to power losses. So we know that the dynamic simulation is performed based on the load flow data that provides us the transmission grid load and generated data in order to assess it and to dynamically analyze it in the worst case scenarios in order to portray a best picture. In this study, dynamic analysis is performed to investigate the WTG's model response subject to grid disturbances. The most relevant disturbance for the study is short circuit fault on the bus. The variable speed, as far as the generation side of the wind turbine is concerned, the variable speed wind turbine using DFIG are more popular technology which is used worldwide due to advantages such as high efficiency, controllability. DFIG is a standard wound rotor induction generator with a voltage source converter connected to the slip rings of the rotor. And during a low voltage event, the converter tries to retain full in control active and reactive power, which is the currents, which is the main advantage of this generator. DFIG can be designed to meet low voltage ride through requirements without external reactive power source. This is the simplest diagram of the wind generation. The gearbox is connected between the generator and the turbine, and the two AC to DC converters are connected in the output processes. Whereas the aims are concerned, the modeling of the Jhimpir wind farm forms integrated into the HESCO-NTDC grid, and load flow analysis and dynamic stability using PSSC software. Objectives of this project was to find out the possible impacts of wind farms integrated into HESCO-NTDC grid regarding dynamic study under the worst case scenarios. And the methodology of our project was to perform literature review, to model wind farms integrated into HESCO-NTDC network in PSSC software, to perform load flow analysis of the wind farms, to add dynamic models and models of the wind farms. So the first results of our simulation was about the data. I mean, to assemble the data and to analyze it properly, so that to have a consistent power flow. In that we have applied a 1 minus n minus 1, we have noted the normal n minus 1 contingency data and over generation data. As you can see in the Zorlu, there is Zorlu MV, there is a slightly less difference from incoming voltage, and these are in the per unit. You can see the Zorlu MV is slightly deviated, otherwise the system is working properly. The system is working properly. And in the 2 bus voltage, the outgoing voltages of the following buses was approximately same. The system was running quite normally, whereas in the n minus 1 contingency, the Jhimpir in the this data, you can see that the 1.0491 and 1.0496, there was a slight difference when the n minus 1 contingency was applied in this way. Whereas the active and reactive power flows are concerned, in the normal, contingency and over generation, there was a slight difference also in the Zorlu power system. In the interconnected system, you can see the active power is 12. In the n minus 1 contingency, it deviated from 12 to 17, and same goes with the reactive power flows. It deviated a little bit. These are the outgoing reactive and active power flow, quite sufficient for the load flow. Whereas there were some differences in the some specific regions, such as FFC. You can see 12.5, there was active power of 12.5. It depreciated to 7.7, it upgraded to 17.8 in the n minus 1 contingency, and remained same in other cases. In the In the dynamic analysis, we conducted a bus fault by giving it a certain fault, certain milliseconds. For example, in this we have given a fault, bus fault of bus fault on the bus 92304 for 100 milliseconds. And this is the comparative analysis of the voltages of the particular TGF and the comparative Jhimpir relation of that, how the voltage behaved when the short circuit was applied on the bus. It somehow tilted, went down and suddenly stabilized itself. Same with the case of power, it is somehow deviated its system, and it stabilized itself after some milliseconds. Well, this is the VAR, values of comparative analysis uh, of the bus TGF and the other Jhimpir. And this behaved like a slight increase in the power VAR, and it went smoothly afterwards. In the while we had frequency disturbances at the same time when we applied fault at the 2930 bus for 100 milliseconds, but it didn't remain for quite long. It just remained for microseconds, I mean 100 milliseconds, and then it disappeared and it stabilized itself. Same is the case with the 200 millisecond. We applied fault at different bus, then afterwards 9428 for 200 milliseconds and check the behavior and check the comparative behavior of the system. You can see the voltages in this system is somehow they lagged, somehow voltages in the certain time, and again stabilized itself after certain time. In the VAR and frequency analysis, these also deviated itself from at a certain point, and but it fault at the 200 milliseconds. While in the fault 3 at bus 8416 for 400 milliseconds, the voltages were quite sufficiently affected, and the power and also the frequency was also affected. You can see the frequency deviations in this slide. As you can see, there's a quite long, very large disturbance for a certain period of time, which cannot be ignored in the interconnected system. Whereas in the conclusion, the load flow analysis was carried out to determine the normal and abnormal flows. N-1 contingency was applied to the system. System remained stable. However, in some instances there were deviations. A dynamic simulation showed considerable deviation in power, voltage and frequency at 800 milliseconds. LVRT approach was observed, showing the stability of interconnected system while disturbances. In the future recommendation, we would like to recommend that the detailed study in the region is required at generation side, because we have focused our study on the transmission side, and the HVRT simulation analyzation is required at the observability region for the protection of region and generation side. And the possible faults have been analyzed at different techniques in the observable region for power loss in worst case scenarios. These are some references, and this is the poster of our project.